Okay, how you all doing today? Well, uh, welcome to another one of our Dean's Distinguished Lecture Series. And today we have Professor Diran Apelian, and he's going to talk about the role of materials, science, and engineering for sustainable development in the 21st century. He's going to highlight some of the opportunities and challenges in this space. Uh, Over the last few weeks, and most importantly, literally over the last few days, I've been getting to know Diran very well. He is a wealth of knowledge, not just on the topic of his talk today, but also, and actually more importantly, on engineering education. I don't know if he'll talk a little bit about that as he speaks today, but he is just a wealth of information and knowledge in a whole host of areas. He received his bachelor's degree in metallurgical engineering from Drexel University in 1968 and his doctorate in material science and engineering from MIT in 1972. He worked at Bethlehem Steel Homer Research Laboratories before joining Drexel University as a faculty member in 1976. And at Drexel, he held various positions, going all the way up from professor to the head of the department to associate dean, and then essentially vice provost of the university. He joined WPI in July 1990 as its provost, and in 1996 he returned to the faculty and now leads the activities of the metal processing entity there. Apelian is credited with pioneering work in solidification, processing, and powder metallurgy, specifically molten metal processing, aluminum alloy development, plasma deposition, spray casting, forming, and semi-solid processing of metals. During the last decade, he has worked on sustainable development issues, including resource recovery, reuse, and recycling. He is the recipient of numerous awards, including a member of the National Academy of Engineering, and from 2008 to 2009, he served as president of the TMS. Will you welcome me today in welcoming Dr. Apelian?
Thank you, Greg. Thank you. Good afternoon, everyone, and thank you for coming to this presentation. Thank you for that introduction, Greg. You took 5 minutes away from my presentation, but that's okay. I was informed that this is the 50th anniversary of this university, UCI, not University of California, but UCI. So in preparation for this, what I thought I'd do is go back 50 years and see what are some of the, and it's not going to be a comprehensive list, but some of the accomplishments that we made as engineers to help our society. And during that, I want to share with you a personal experience that I had about 10 years ago. Because all my career, I have worked in the space of manufacturing and making things, metals processing. Most days it's metal processing, a couple of days of the year is metal processing, but most of the time it's metal processing. You know, metal casting, silicification processing, manufacturing, thermal processes, plasma spray, making things. And about 10 years ago, I was asked to give a talk that was brand new to me. It was in the area of materials and society. It was the ASM Distinguished Lecture on Materials and Society. And it was the kind of thing that I didn't have anything on. I had no slides on this, nothing. It was brand new. And it was a wonderful time. It was in the summertime, so I had time to reflect, read a whole bunch of things, and put together a story. And I came to the realization that most of my career I had spent in making things, and most of the funding was coming from Department of Defense, DARPA. Not that it's bad, it's all good. But some of the real challenges of our society, energy, food, water, health, the kind of funding for these areas from the materials perspective was not there. So that became the storyline of how we need to look at what we are making and how we are using the materials by which we're making these components and what happens to these components at the end of life. So it's not really about recycling, it's about recovery of the elements that we use from the periodic table and reuse them, in other words, recycle them. So that's essentially the premise of the talk, the introduction to the talk, and leading to I'm going to paint you the picture of what the situation is, what the context is, what's the problem, if you will, and what are some of the solution paths. I'm not going to talk about the problems, I'm going to talk about the solution paths. And they fit into three categories, three axes, three channels. One, education. The other one is technology innovation to do all these things. And the third one is policy. And all three of those have to happen concurrently or in sync with each other. So I'll talk about those. And that's really a very quick summary. So if that interests you, stay. If that doesn't interest you, that was a great time to exit while I'm going back to my screen. So 50 years ago or so, or in the last 50 years, 55 years actually, and as I said, it's not a comprehensive list. But if you look at that list, it's pretty amazing. At least I was impressed with it. Of course, it's material-centric because that's my background. So what are the kinds of accomplishments we have done and help society through development of materials? I mean, just think about how many of you wear soft contact lenses here in this room? Usually there's at least half the room that does it. These things didn't exist 50 years ago. You know, today we do an MRI, we take it for granted. The launch of the Sputnik was a big deal when I was growing up. That actually inspired me to be an engineer and, more importantly, to go into the materials area, actually metallurgy at the time. Lasers, we take it for granted. So anyway, I just wanted to put that list. I'm not going to go through each one of them. Actually, you could spend a lot of time in each one of these, but when you look at that list, it's pretty impressive. However, as we have accomplished these wonderful accomplishments, there's something else that has happened in the world in the last 30 years, not 50. And it's a good thing. It's a good thing. The developing countries, if you look at it 50 years ago, if you looked at China 50 years ago, you looked at India 50 years ago, and where they are today, they're far ahead of the game in the sense of more people have more disposable income. Quality of life is much better for a lot of people. Unfortunately, there's still some places in the world where quality of life is terrible. But if you compare 50 years ago, a lot of people are doing a lot better than they were before. So I'm not a historian, but I think, my premise is that, someday they're going to look at this era where in a very short period of time in the history of civilization, that's nothing, 30 years is nothing, where the quality of life increased dramatically for a large segment of the population. So that's a good thing. However, the consumption and the use of things has become to the point where sustainable development is probably one of the grand challenges of the 21st century. You probably have heard a lot about this in terms of population growth, but in a nutshell, just let me recap it here. We entered the 20th century with 1.6 billion people and exited, it's a 100-year, and exited with 6.1 billion. And many of you and the young people in the room here, in another 20 years when you're in your 40s or early 50s, it's going to be 9.2 billion. So more people, more consumption, and I'm not talking about climate change alone. That's also an issue. I'm talking about use of materials. So this is the hierarchy of needs, Maslow's hierarchy of needs of society, if you will. We need energy. We need water, we need food, as I said earlier in the introduction, housing, mobility, all of these things are important areas. But if you look at the amount of money that's devoted to R&D in these areas compared to defense, it's pretty dismal. We're spending in the world today, in the planet Earth, every 24 hours, $3 billion to defend each other from each other. If you take the budget of the Defense Department of USA, the Defense Department of Japan and India, which has a very large defense budget, China, Russia, you add them all up. This is arithmetic. And you divide by 365. You get about $3 billion every 24 hours. If you look at how much money is being spent in these areas, it's minuscule in comparison. The other thing that has happened with population rise, consumption, quality of life going up, is that we're using more and more of the periodic table. The computer chip, this is from Intel, back in 1980s, 11 elements of the periodic table. A few years later, 1990s, 15 elements. And now, in the 2045 elements, and the most recent data is over 50 elements of the periodic table. This is just a chip. So to visually portray that, we're using more and more of the periodic table to make more and more complex components. So it's no longer the Bronze Age or Iron Age, it's the everything age. And if you take a smartphone, whether it's a Samsung or an Apple, it doesn't really matter what kind, it has over 59 elements. 30, 40 years ago, people like me and the first row here, it was structural components, integrity. Now it's functionality. You take your phone, you go like this with your fingers, things get smaller, they get bigger. Electrons, right? It's a different ball game. Now, where do these things come from? You can't buy these at Home Depot. You can't buy it at Amazon. You got to get it out of the earth, and you got to reduce them because they're all oxides and use them. To give you an idea, and this is an older slide, but it's not a smartphone, obviously. It's a Nokia first generation. There are a lot of elements in these things. I think you get the picture. We're using a lot of the periodic table. But then you do a very simple calculation. These are cell phones, and there are over 7 billion cell phones in the world today. And this is 1,300 million units at 250 milligrams. So there's about 250 milligrams of silver, gold, 24 milligrams, not much. 9 milligrams of palladium, which is very expensive, copper, cobalt. But when you add them all up, that's 325 tons of silver. That's a lot, and that's very conservative numbers, as I said. When you look at laptops, it's similar. So there's a lot of electronic components that have considerable metal stock, that is not being recovered and reused. The notion of recycling by putting it in a bin someplace doesn't necessarily mean that it's being recovered and reused. I want to get off tangent for a second. A lot of electronic components today, the solutions that I'm going to talk about later about policy, technology, education, it's fragmented. Every country has its own rules. You go to Germany, they've got a very strong policy. Finland has a strong policy. Norway has a different policy. France has a different policy. USA has a very, very different policy. And the solutions to these issues have to be global solutions. They cannot be nationalistic or centric to one country. So as you see, there's a lot of material that's not being recovered. And in the USA right now, we ship a lot of these things to other countries where there are no EPA, no regulations. They burn them, toxic fumes, et cetera. It's not a good situation. The United Nations did a study of end-of-life recycling rates. And this is the 2010 data. I should have put the 2012, but it's the same data, which is symbolically important as well. But if you look at the elements there, at the very bottom, if you're colorblind, let me help you. This is less than 1% recycling rate, 1 to 10%, 10 to 25, 25 to 50, and greater than 50. But these are the rare earth elements. That's less than 1%, and 98% of the rare earth elements are imported from China, so we don't make them here. So the recycling rates are pretty low. It's certainly not acceptable, and it's not sustainable. EPA data about 2 years ago, 2010, recycling rates in the U.S., and actually the 2014 data is not that different as well. PET bottles, about 21%. Glass containers, 33%. Tires are 35.5%. Every place you see white, that's an opportunity area. There's one data point that stands out, and I wish every one of them was that way, and that's auto batteries. These are the lead acid batteries, and that has a recycling rate of over 96%, which is really good. And you ask the question, why is that? Why is that so high and all the things are lower? Well, there's a policy by the federal government. That's where the policy comes in, that lead is bad. There's a collection system that's built and a business model where people are making money at it. So the one thing that I want to insert here is that the solutions for sustainability, a sustainable solution for sustainability has to have a sustainable business model. If the company is losing money, it's not going to make it. So the auto battery business is a very profitable business. It helps that the cathode and the anode are not too complicated, so you can actually do it economically. It's feasible. But also there are two things to take away from here, that it can be done if policy, innovation, and education all come together, and that there are tremendous opportunity to have an impact in our country. So, it's really not an option. It's something that needs to be done. From an energy perspective, the production of the energy cost of production and the carbon footprint is a serious matter. Just a couple of examples. And what we're plotting here is megajoules per kilogram. This is for aluminum. I don't think it comes out very well. So let's just take two, aluminum, and let's take platinum. The burgundy color is the amount of energy you have to put in to break up the oxides of the ore and make that metal. To make aluminum, 1 kilogram of aluminum, I need 200 megajoules of energy. However, if I take the scrap aluminum and remelt it and recast it, I can save 95% of the energy. So if you just forget about the periodic table discussion we just had and just look from an energy perspective, it sure makes sense. So a couple of more things to amplify and elaborate on this theme. Look at metal production trends. And this is very good data, hard data to get, by the way, on a variety of different elements, different colors. And if you can't make out the elements here, let me help you out here. Zinc is in the blue in kilotons. Iron ore is the burgundy color one. Copper is the red one. But one thing that you notice is that between this period that I was talking about, where quality of life on the planet increased a lot by the developing countries, et cetera, look what's happening to the consumption. So I'm building the story here and weaving the story, if I may say it that way, where increasing population, more consumption, the metal production is really going up. So where does all this stuff come from? Well, it comes from an ore. And the ores are dug up from the earth. And if you're not in the language of metallurgical or extractive metallurgy, the ore grade means how much stuff you have to dig out to be able to get that element. So the ore grade, if it's high grade, you don't have to dig as much out. And as the ore grade gets lower, you got to dig a lot more stuff out of the earth to get the element. And that's going down. So you got two things going in opposite direction. As you saw here, metal production is going up, and the ore grades going down. So not a good recipe for sustainable, to continue this way. The other thing that we're seeing is commodity prices. Now, right now, with what's happening in China is not the best example, but this is just perturbation. But the commodity prices have increased sharply since 2000. And you can see that here. And this is data from McKinsey last year. And if you look at, assuming a compounded annual growth rate, CAGR about 1.8%, looking at four things: metal ores, light blue, fossil energy, biomass, and non-metallic minerals, between 1980 and 2020 estimated. During that time frame, the percentage change for metal ores is 200%. So metal production, as you saw from the few graphs before, is in demand because of the supply. I mean, there's only so much on the planet Earth. We're using more and more of the periodic table. And then comes the critical materials. And what are critical materials? Critical materials are, you need it and you cannot have it. You know, there's not enough of it, so it becomes a critical material. It becomes not precious, critical. Much of it is dependent on geopolitical forces, and these are materials like neodymium. If you're not in it, neodymium is used in high-performance magnets. Emerging uses are traction motors, electric vehicles, wind turbine generators, a whole bunch of applications where neodymium is used in. Terbium and europium, LED lights, CRTs, flat panel displays, etc. Very important elements. Now, if you don't have this available, if they're not available, or you can't get them, it can create havoc. For example, the T5 fluorescent lamps, their development was delayed for 2 years because manufacturers, shortage of the europium and terbium supply chain. In wind turbines, they also had major setbacks because of that. When I talk about geopolitical forces, I can't think of a better example than to show this one here. I think it's going to be difficult to read this. Let's go to the next one. Rare earth metals, and I'm just picking 5 of them here: cerium, samarium, lanthanum, neodymium, yttrium. In a period where China decided they're not going to export it, and they're going to limit their export of rare earth metals, they produce 98% of the world rare earth metals. In a period of 6 months, and we use a lot of cerium in our lab, it went, increased, 700%. And there are not too many things that increase with that rate, right? It's crazy. The prices are way down now because they relaxed the situation, but nevertheless, it's an issue. So there are a bunch of elements that are critical. These are the list of critical materials where we have limited supply, and meaning if we do not reuse these materials, we don't recover them and reuse them, we're going to have pay a very large price in the future. Tantalum is another one, very biocompatible material, very important for prosthetics. Platinum, scandium for alloying. These are neodymium, the second one, gallium. These are very important materials. I'm not sure how many of you know this, but before 1980, and this is another one, I'm using this because of the policy. Before 1980, USA was the largest producer of rare earth metals. That's production, kilotons, year, and this is the Mountain Pass in California, Molycorp Corporation. EPA came in, this is policy, said you cannot continue your operations by the leaching that they were using to get the rare earth metals out was damaging the environment, the earth. So they said you can't operate this way. And the cost of meeting the needs that EPA was mandating, they couldn't stay in business. So they shut the mine down. So essentially we didn't produce, we produced some, but as you can see, it went way down. At the same time, China opened its doors, and China has rare earth mines. And also they don't have EPA. And look what happened. So where we are today, USA is producing very little of the rare earth elements. It's mostly coming from China. So when you are relying, if you're a company and you're relying on these materials, and it's all coming from China, you have an issue with it. Magnets, I think many of you know what this is, but again, just to give a historical context here in this kind of a presentation, which is more broad. 20, 30 years ago, we didn't have the iron neodymium magnets. It was alnico, and then the ferrites, and then samarium cobalt magnets. Some of you may remember that. And this is done geometrically where the size, the volumetric size, is kept fidelity, showing that to get a magnet to generate 1,000 Gauss at 5 millimeter from the pole face, you only need 0.2 centimeter cube volume of a magnet, whereas in the alnico, it's dramatically more. So we have a lot more smaller magnets, more powerful, and they're used in a variety of different applications. This is one of my colleagues who's actually working in recovering the neodymium out of the rare earth magnets. An average car has over 35 magnets. And when cars at the end of life, they go to the scrapyard, they get shredded. And they get sorted into non-ferrous and ferrous. And not only cars, but also construction materials, LDV, or household appliances. They get shredded. If you've never seen one, it's an amazing operation to see. And they get separated using eddy current and other sortation techniques into non-ferrous, which is the non-magnetic, that has the aluminum, copper, tin, everything that's non-ferrous. All of this is the ferrous. And the rare earth from the magnets ends up here. And we've got a major program to recover these from the steel companies and the slag operation. Very successful. Lithium-ion batteries is another one. I'll skip that. So I think you get the picture that we're using more and more a periodic table, not recovering these. So what to do? What's the situation? I did say that I was going to provide some solution paths in 3 areas. One is education. One is the innovation, the technology that has to be developed. And the other one is in the policy area. So let's talk about the education first, and then talk about the innovation technology space next, and thirdly, talk about policy. In the education space, what we have done for our by the way, we have a consortium at our university. It's a multi-university consortium in the Materials Resource Recovery and Recycling. It's an NSF IUCRC, Industry University Cooperative Research Center, with WPI, Colorado School of Mines, and KU Leuven in Belgium. Each of these universities brings quite a bit of expertise to the table, and we'll also be bringing in University of Tokyo in the very near future, so 4 universities. And now with University of California, Irvine, UCI, with Dele, and hi Dele, I'm glad you came, and Julie Schonung, we just did a pre-proposal for the Engineering Research Center because they bring in the policy part, very important to this. So in the education part, we work with our consortium members to learn together, of course, but also to learn from some systems where over the years they have shown to be sustainable. And the best example is nature. Nature, the natural ecosystem, has been around a long time. You look at these trees that are shedding like crazy, and if the people don't pick it up, a year later they will degrade, they'll go back to the earth. A cherry tree is a perfect example. The natural ecosystem is a great, great teacher. We can learn from it. So in our consortium with the corporations, and I'm a capitalist, okay, that's why I'm not saying that we're going to give up and go back to the village and just wear garbs, but we can learn and apply to the industrial system. But if you look at the natural ecosystem and try to learn from it, it has, it's a closed loop system. There's no waste. If you think about it, there's no waste in nature in that sense. Whereas an industrial system is usually open loop system. There are a lot of subsystems. If you work in the civil engineering space, for example, if you look at how the watersheds are and how the, or go to the Everglades and see how all the subsystems and how they all feed on each other. And but industrial systems, they don't have a lot of subsystems. It's cyclic. It's not linear. And unlike what I've been talking about the last 10 minutes, nature uses very few elements. If you look at your bodies alone, it's mostly carbon, oxygen. There are not that many elements. Industrial systems, as I just showed, use a lot of the periodic table, especially in the last 20 years. And again, this is a phenomenon that has occurred in the last 20, 30 years. It wasn't like this years ago when the population was even lower on the planet Earth. If you remember how your grandparents lived, I don't care how poor or rich they were, they didn't throw anything away. They reused it. Again, I'm making some of the younger people in the room very uncomfortable here. I can see the two of you back there, ladies. But, in the older days, meaning like 40, 50 years ago, people repaired their shoes. They resold them. Things got repaired. They fixed them, and they reused them. Now where everything is a throwaway. I went to school, we had to use a fountain pen to do our homework. Now everything's a throwaway pen. I still use a fountain pen. I've had the same damn thing for a long time. I just put ink in it. So it's a different way of thinking about the world. And the cool thing about the natural ecosystem, that the index of well-being in the natural ecosystem is equilibrium. In the industrial system is all about growth. So I'm not saying let's give up growth. I'm not saying but there are some things you can learn from here. And the first thing you learn is reduce waste. Reduce waste. Make things that will last a while. Make things that are repairable. Make things that can be disassembled and be fixed. I'm sure you all have a personal story about things that you have bought that cannot be repaired or fixed. So that's one thing we're doing. And essentially, if I could put it in a sentence, it's the cradle-to-cradle approach. Greg mentioned in the intro about the innovation, education activities that we're doing. We have a first-year experience for our students now. It's only 5 years old, but amazing results, where every student that comes in the engineering, as well, actually the whole university, but let's say in engineering, does a course in the first year. It's not physics, math, calculus, and chemistry, but that have to do with engineering. So they're exposed to, we have 6 of these courses. I'm going to only talk about one of them. One is recycle the world, one is heal the world, one is feed the world. They're all societal issues. So the students who take the course that we've developed, this course here, is taught by 2 people. One person in the humanities who brings a completely different viewpoint than the character in engineering. And they're not rehearsed, so they're not lectures. The material is given, uploaded on the course website. The students read that ahead of time. And the meeting, the 2-hour meeting twice a week, it's a discussion period. It's interaction. Actually, sometimes it's uncomfortable because you don't know what questions you're going to get, but you got to be okay with that. And if you can't answer, you say, I don't know. We'll figure it out. But it's a completely different way of learning. Nobody falls asleep. It's always fun. It's like improvisational theater or comedy, But it's a great way of getting into the discussion. It's like the way Oxford and Cambridge used to run in the old days, where you had more discussions and tutors, mentors. We have 4 PLAs working with us who've taken the course before. So in this course, they spent a term, 7 weeks, in reading, exams, questions, discussion, and the B term, they do a project. They do a project in this area. So we're doing quite a bit in this area. It's part of education. I already mentioned the Center for Resource Recovery Recycling with the 3 schools and the ERC that hopefully we will be successful. And it'd be great if we have that. And just to show you the kinds of companies that are involved here, Alcoa, of course, in aluminum, Red Mud, AMRT, Rubis from Germany and copper, Constellium from France and aluminum, DMVGL from Norway, they're in materials, shipbuilding, General Motors, Global Tungsten Powder, the Planzy Corporation, they make all the LEDs. It used to be the old Sylvania plant, Hydro and aluminum. Anyway, I think you can see the list of companies, very diverse. They're not all from the same group, but we're nucleating, if you will, a culture where recovery of materials and sustainability is the agenda. It's been a lot of fun doing this, and we're looking forward. Hopefully, we will get the CRC. And if we don't, we have Della, Julie, and I have a recycling plan where we're going to we have a contingency plan as to what to do with it. But hopefully we'll win. We'll see. So I think education is. I've talked about the freshman year. I've talked about the consortium, but also at the public level, at the layman's level, at the just general education is also important. I didn't talk about that, but it's very, very important. What do you do with your batteries when you're done with it? Just getting the idea across that if they end up in a landfill, and if it rains, and all these landfills leak, that it can do a lot of damage. Just the public education in terms of how to dispose of things. And I'm not, batteries, nail polish remover or paint removers, all of these things, chemicals. Unfortunately, a lot of them are ending up in our landfills. So education at all levels, from K to 12, high school, public, university, and corporations. At the innovation level, the technology, remembering the slide about the natural ecosystem, industrial ecosystem, the portfolio of research for the CR Cube is actually, I'm not going to go into the detail, but just see the framework. So we spend a lot of our energy in assessing and identifying opportunities where we can reduce production waste. And what do I mean by that? Every pound of aluminum that's made, there's 3 pounds of red mud that's made, and that's landfilled. They don't know what to do with it. 1 pound of aluminum, 3 pounds of red mud. Red because there's a lot of iron in it. It looks red. But there's also scandium. There's also all kinds of very important elements. But so far, they haven't invested in how to figure out how to recover all these things. And we're actually doing that, where it's becoming feasible, economically feasible, so that a sustainable business model can come up. Post-consumer waste, I think you know that, all the stuff that we use, what happens to it at the end of life. And then we're developing measures, controls, instruments, laser-induced spectroscopy, X-ray fluorescence, sorting things by their chemistry, not by magnetic or non-magnetic. The most difficult one is this. How do you convince corporations and companies to design and make things that can be taken apart and repaired? I love Apple products, but they're one of the biggest culprits. I can't even take the battery out of my iPhone. Because the first thing you have to do when you recycle, you got to take the battery out. Otherwise, you'll have an explosion. So those are the kinds of things we work on. Just to give you some examples, production waste, aluminum, for those of you who are not in metallurgy or metals and other disciplines, it takes a hell of a lot of energy to take the bauxite out of the earth, the aluminum oxide, Al2O3, and to make it into aluminum, you got to put a lot of energy into it. And when you do that, you produce these red mud landfills. This is where the plant is, and those are the red mud landfills. So a lot of effort is going into, and this is just one example. There's a lot of examples like this where we are making things and producing a lot of waste and not worrying about recovering all the good stuff in the waste. So whenever you take waste and create value, You're doing all right. Post-consumer waste. There's a lot of stuff that goes out there, and actually, I forgot I had this slide. So if you look at the landfills, there's a lot of stuff that ends up in the landfills. And, just pick a couple of them, varnishes. People throw these things away, adhesives, spot removers, art supplies. Yeah, art supplies. And all of these things that you see in the middle have these chemicals in them. And these chemicals have an effect on the right side, and I got to tell you, there's nothing good on the right side. There's absolutely nothing good on the right side, but that's what ends up, the ramifications of these ending up in landfills when it rains and they leak and ends up in the water system. It's not a good thing. But the good side of the story is that some of these landfills can be urban mines because there's a lot of stuff in them. And in fact, there are programs to mine these landfills for what's in it. And to give you an example, if I dig out 1 ton of gold ore from the earth, I will be able to get about 35 grams of gold. So, you can see the difference. But if I do the same thing with a ton of used cell phones, it's a magnitude order difference. So there's opportunity to really mine these landfills, urban mining we call it, and there are people working on this area. So some of the enabling technologies to finish things up here is tremendous computing speeds, which is allowing us to do mass migration, computer recognition techniques, computer and sensor technologies, a lot of great engineering work, innovations that are enabling us to do these things. So, for example, when you have scrap, aluminum has all kinds of alloys in it. We need to be able to differentiate between the alloys. Now we have technologies like X-ray fluorescence, where the scrap material comes on the conveyor belt. We can detect what's in it. It's not showing here because it's proprietary. And using pneumatic hammers, we separate the scrap into its original components. 356 alloy goes over here, 380 goes over there, 390 goes over there, and just remelt them and reuse them. So you save energy, you recover, you reuse. It's fantastic stuff. Policy. Policy is the last piece here to finish things up. Very critical, very important, because it's human behavior, and much of it is dictated by the rules of the land, the laws, and policy. I think I was overly ambitious to put this in. I wanted to talk about circular economy. I'm not going to have the time to do that. Let's not do that. But manufacture for disassembly and having companies and engineers and people who make things to have the end of life in mind at the beginning, at the onset, is something that is probably our largest dilemma or impediment right now. When you buy a product, I don't care what it is. It could be a car. It could be an iPhone. It could be a computer. Whose responsibility is it to dispose of it at the end of life? This is a conversation we could spend a lot of time on. Ben, you got a car, right? So when it dies and at the end of it, what happens to it? You got to worry about it because it's your car. You bought it. In Germany, it's completely different. It's a manufacturer's responsibility. You can actually take your car to the dealership and they've got to take it back. Not yet. Next year, that's the law. And guess what? It's not a good week to talk about Volkswagen, but a bad choice. But the Audis of the world, the BMWs of the world are spending a lot of time in designing cars in such a way that they're going to end up with it. It's not going to be your problem. It's going to be their problem. So they're looking at how to put things together. Do they weld it? Do they rivet it? Do they use glue? So they can disassemble it, and how to reuse it. So it's changing complete paradigm. Just one regulation. So as I said, I'm not going to have time to go into the circular economy, but well, I'm not doing justice to this. I should. So just take a look at this. Landfills down here, energy recovery, collection, service provider. At the very top is the mining and the parts manufacturers. There's a chain that goes through. And every one of these, you could put policies in that will change a paradigm. Imagine having manufacturing for disassembly as a focus, or modularization or standardization. What it will do. Imagine having one charger that will charge all the electronic components you got. Just one thing. I gotta carry this whole bag of stuff when I'm traveling. American Express card and this gadget of stuff are designed to last. Oddly enough, the one company that's doing this has nothing to do with manufacturing. It's Patagonia. Patagonia and its CEO has written a new book recently where if you have a jacket, or they're expensive, they're not cheap, but if it needs to be repaired, you go into the store and say, this thing is getting old, I want to buy a new one. They will talk you out of buying a new one. They will repair it. And what they're finding is that they're getting tremendous loyalty. Well, first of all, people who buy Patagonia jackets, they're more enlightened people, and they got tremendous loyalty. So doing the right thing and doing good actually pays off, and it's the right thing to do. The other area is this area of performance contracts, new business models. This is where the manufacturer is responsible, not you. So McKinsey is actually doing a study with GM right now where, with your phones today, you have a service, you have a monthly service, right? You pay money to Verizon, AT&T. It's a performance contract. Imagine if you do that with your car. You don't own the car. You have a performance service with whoever, Ford. You guys always have good weather here, but in Massachusetts, in the summertime, I can have for 3 months a convertible. In the winter, I can have an SUV. It's a pretty cool idea, but that's going to change the paradigm. So if GM is responsible for the goods, they're going to end up with it. Trust me, they're going to build and design, build, and recover them very, very differently. So there's a lot of, it's a very fertile terrain right now, a lot of opportunities, and it's a great space to work in. So to finish things off here, I don't want to take more time than I need to. I spent quite a bit of time in the introduction to set the context of what's happening, but I firmly believe that these are 3 areas that you have to work in, and not in series, but in parallel. And it's going to take a variety of different people to do that together. But it's a very exciting area to work in, and hopefully we'll do this ERC with Irvine. And in closing, I want to thank you for your attention and for coming. I even got some Arabic in there, Syed, just for you. Yes, first-year students. What we found out 5, 6 years ago is that a lot of students were getting turned off, who came in, they had a very high activation energy after high school graduation. They got into the university. They impressed their relatives, their parents, they got into university. And they don't know enough, but they pick a topic, mechanical engineering. They heard it's cool stuff. And they come into university with this excitement. But we don't do mechanical engineering the first year. They got to take physics, they got to take chemistry, they got to take math. And unfortunately, I have wonderful colleagues at my university like you guys have here. And the math professors, they say, I'm going to get the kid for 1 year. Yeah, get all the math they need to take. So it's very intensive and all good stuff. Fundamental, basic sciences. It's important. At the same time, what we're doing is losing the opportunity of that activation energy that exists, that ignition point that they need to ignite their aspirations, their curiosity. We're thwarting it. So with this course, what we've done is expose them to some major societal issues. We know they're not going to solve them, but they're going to get hooked. And also they're going to realize how little they know. So knowing what you don't know is a really valuable asset, right? Now you're getting into the nitty-gritty. That's the course that we could not mandate. So because of the discussions, the physics professor saying, oh my God, you're going to take something away from me. And the chemistry professors get even more. So we piloted it. We figured that the way to do this is not to say, we're going to take something away from you because the students need it. It's for the customer. The customer needs it. I don't care about you. The customer needs it. We didn't do that model. We said we're going to pilot it, see how it goes. So the data, retention rates at our university right now in engineering is like over 95%. 95% students coming in are still in. Their performance in the projects are way up. And, people are saying, hey, this is cool, it's working. So to answer your question, they get A term and B term. A term, they get 3 credits in engineering science 1000 level. And B term, they get 3 credits in the humanities and arts.